In this video, we'll be looking at section 8.1c, which covers applications of the law of sines and the law of cosines. First up, to find the distance across a small lake, a surveyor has taken the measurements shown. Find the distance across the lake. So it looks like the surveyor stood here and determined it was 800 feet to that side, 900 feet to that side, with a 70-degree angle in between. I'm going to let the distance across the lake be D. So this is a side angle side case. Side angle side is when we use the law of cosines. So using the law of cosines here, I'll have D squared is equal to 800 squared plus 900 squared minus 2 times 800 times 900 times the cosine of my angle, which is 70 degrees. Typing all of that in, we have 800 squared plus 900 squared minus 2 times 800 times 900 cosine of 70. That's D squared. So if I square root that answer, I find that the distance across the lake is 978.5147, and we were measuring in feet. Next up, we have two satellites. The path of a satellite orbiting the Earth causes it to pass directly over two tracking stations, A and B, which are 69 miles apart. When the satellite is on one side of the two stations, the angles of elevation at A and B are measured to be, it should be 83.9 degrees and 86.2 degrees respectively. How far is the satellite from station A, and how high is the satellite above the ground? So right now we're missing the fact that these are 69 miles apart, so I'm going to label that. I want to find the distance to station A, so I'll call that A. And I also want to find the height off the ground, which will be the vertical distance straight down, and I'll call that H. First up, let's find A. Well, wait a minute. To go from flat ground to flat ground, a straight angle all the way over should be 180 degrees. So this angle right here should be 180 minus the 86.2. So if we do 180 minus 86.2, we get this angle here to be 93.8 degrees. I now have angle, side, angle. I can find this third angle and then use the law of sines. So if I take 180 minus the 93.8 that we just found, minus the 83.9, which is the angle from satellite A to the ground, we get that this tiny angle up here is 2.3 degrees. If I set up the law of sines, then the sine of that 2.3 degrees over its corresponding side 69 is equal to the sine of this angle over here, 93.8, over its corresponding side A. And I'm trying to solve for A. If I cross multiply, then 69 times the sine of 93.8 degrees is equal to A times the sine of 2.3 degrees. And if I divide both sides by the sine of 2.3, I get A is equal to 69 sine of 93.8 divided by the sine of 2.3. It looks like the distance we are from satellite A is 1,715.5551, and we were measuring that distance in miles. But we also want to find the height above the ground. So I drew this line straight down to the ground, and that actually makes a right triangle. I know my A length, and I know my A angle. H is opposite. So if H is opposite and A is the hypotenuse because this is a right triangle. Opposite and hypotenuse, that's sine, because the SO from SOHCAHTOA tells us that the sine of our angle, 83.9 degrees, is equal to the opposite side, H, over the hypotenuse side, which is A. That's what we just found, 1715.5551. If I multiply both sides by that 1715.5551, I get H is equal to that number times the sine of 83.9 degrees. And I get that the height off the ground is 1705.8415 miles. Next up, a 113-foot tower is located on a hill that is inclined 34 degrees to the horizontal. A guy wire is to be attached to the top of the tower and anchored to a point 98 feet uphill from the base of the tower. We want to find the length of the wire needed. So I guess length, I'll call it L. I'm going to kind of redraw this picture because I think it's going to help me really nail down what I know versus what I don't know. So we have the ground, which is not level. We have the ground, and we have the hill. We know that is at an angle of 34 degrees. We have this tower that's vertical with respect to flat ground. That's 113 feet tall. We know that there's going to be this wire here that attaches 98 feet up the hill. So the question is, what else do we know? Well, if I go from flat ground straight up, that whole thing should be a 90-degree angle. So if I take 90 minus the 34 that I already know, there's 56 degrees from my hill to straight vertical. But hey, my hill to straight vertical, that's this angle as well. That's 56 degrees. So I now know a side, an angle, and a side. Side, angle, side allows me to use the law of cosines. This is my L. Using the law of cosines, we get L squared is equal to 113 squared plus 98 squared minus 2 times 113 times 98 times the cosine of my angle, 56 degrees. Typing all that in, we have 113 squared plus 98 squared minus 2 times 113 times 98 times the cosine of 56. That should be my length squared. If I square root it, we get that the length of wire needed is 99.9408. Let's try one kind of similar to this, but also similar to the satellites. A pilot is flying over a straight highway. He determines the angle of depression to two mileposts that are 4.3 kilometers apart to be 32 degrees and 56 degrees as shown in the figure. Find the distance of the plane from point A and the elevation of the plane. All right, I'm actually going to reference geometry again. Hopefully you'll remember this. If not, hopefully you'll understand why it's true. So it's 32 degrees to go from the horizontal down to this B. It's going to be equal to this angle, 32 degrees, because if you look from the horizontal up, it's 32 degrees. The way we talked about that in geometry would have been alternate interior angles are congruent. Don't worry, I'm not going to test you on that. But it just kind of helps us a little bit so that we have another angle to work with. The angle from horizontal down to angle A is 56 degrees. So that means this is 56 degrees. But hey, if I know this is 56 degrees, I can find angle A, the inside one over here, because that's a straight line. If I take 180 minus the 56 degrees I already know, then this angle is 124 degrees. Well, hey, while I'm at it, why don't I find this angle here from B to A? The whole thing is 56. This little one is 32. 56 minus 32 tells me this angle is 24 degrees. Let's just find all the angles. Why not? We know that A and B are 4.3 kilometers apart. And I want to find the distance to A. So I have an angle and its opposite side. I have the angle and I'm looking for its opposite side. I can use the law of sines here. Because the sine of 24 degrees over its opposite side, 4.3 kilometers, is equal to the sine of the 32 degrees over its opposite side, A. And that's the first thing I want to find. Cross multiplying, I get A times the sine of 24 degrees is equal to 4.3 times the sine of 32 degrees. Dividing both sides by the sine of 24, we get A is equal to 4.3 times the sine of 32 all over the sine of 24. Side A is equal to 5.6023, and we were measuring distance in kilometers. We also wanted to find the elevation of the plane. That's how high it is straight off the ground. Well, straight off the ground, that makes a right triangle. I know this side, and I know this angle. I want to find height, which is opposite. So the opposite and the hypotenuse, that's sine. The sine of the 56 degrees that I already know is equal to the opposite side, h, over the hypotenuse, that's length A, which I just found. Multiplying both sides by 5.6023, we get h is equal to 5.6023 times the sine of 56 degrees. 5.6023 sine 56. The height off the ground is 4.6445, and again, we were measuring distance in kilometers. Getting close to the end, we're going to look at two more. First up, two planes leave the same airport at the same time. One flies at 20 degrees east of north at 500 miles per hour. The second flies at 30 degrees east of south at 600 miles per hour. How far apart are the planes after 2 hours? These can be kind of hard if you don't know your directions, so I'm going to start by just kind of laying out north, east, south, and west. You have north, east, south, west. The first plane is flying 20 degrees east of north. So you start north and turn 20 degrees eastward. So we know this is 20 degrees. The second flies at 30 degrees east of south. So we start at south, turn 30 degrees east. And that's kind of what we're looking at. We want to find the distance between these. I'll use D for distance. Why not? I'm going to call this plane A, just so I have something to call it. Plane A is flying at 500 miles per hour. Keep in mind, distance equals rate times time. It's flying at a rate of 500 miles per hour. and it's flying for 2 hours. So in 2 hours, this plane will have traveled 1,000 miles. Then we have plane B over here. It's flying at 600 miles per hour for 2 hours. So if we take its rate times time, that plane has traveled 1,200 miles. So it looks like I know 2 sides. I don't know the third side. Maybe I can find an angle going on in here? Well, all the way from north to south is 180 degrees. If I take away the 20 degrees and the 30 degrees that I already know, that leaves this middle angle to be 150 degrees. If I know 2 sides and the included angle, I can use the law of cosines. That'll give me d squared is equal to 1,000 squared plus 1,200 squared minus 2 times 1,000 times 1,200 times the cosine of my angle. And I can type that in. 1,000 squared plus 1,200 squared minus 2 times 1,000 times 1,200 cosine of 150. That's d squared. So if I square root that answer, these planes are 2,000. Whoops, I typed something wrong. 1,000 squared, 1,200 squared. Maybe not. 2,125.6672 miles apart. I don't trust that answer.